Hello there, this is David, Director of Marketing and Communications at Kaduk Musical Instruments. And today I am joined by no other than Thomas Kaduk himself, the founder of Kaduk Musical Instruments. Well, we are here today to talk about the piano and specifically about the physical principles behind the piano. So how does the piano function? And we're going to talk about different components in the piano. And today the plan is to talk about the piano soundboard. So the piano soundboard, what is it? What is it for? And scientific principles are behind the way it works. So that's the plan. Well, let's get started.
Okay.
The soundboard. Well, what is the soundboard? For those of you who don't know anything about pianos.
Yes, well, the soundboard is indeed good that you say that you ask. The soundboard is the wooden plane behind the strings, and the soundboard is the thing that you actually hear. So, what the soundboard basically is something very similar to this, because when I do this, you hear me louder.
Yeah, so if you make a funnel with your hands in front,
Yeah,
you talk like this instead of this. Okay.
yeah.
What is happening?
And so our microphone is here.
Yeah.
If I do this towards the microphone, then for anyone it will be obvious that it is louder.
Yeah.
But the interesting thing is that it is also louder if I do it in that direction. So if I now talk off mic, it's softer than if I talk towards the mic. But as soon as I do this, then it is much louder for the mic, even though it's not in the direction of this line of this funnel.
Okay. So and what principle?
Impedance matching. And that's basically what the soundboard is doing. So there is a certain impedance of the how do you say that?
The
in
vocal
English?
cords.
Vocal
Yeah.
cords
Yeah.
with the air, which is already matched by the cavity in the mouth, etc. But it is better matched even with this funnel. So basically what the soundboard is doing is it creates an impedance match between the strings and the air, and therefore the energy in the strings can pass through the soundboard, through the air.
Okay. So an impedance match. Maybe we should explain what impedance is then.
It's something similar to resistance, but resistance is something that you use in a linear system or in electronics with a DC system, direct current. And impedance is the sort of hinder or impedance that is there for oscillating systems, for systems that go
Yeah, that
back
have
and forth.
yeah. So waves, for instance, sound waves. In
Yes,
this
yes.
case. Yeah.
So first of all, it matches the impedance to the air. That's one of the things it does. So because of the soundboard, you can hear the energy that is in the strings after you hit the string. Second thing it does is it stores the energy for you, or it helps to store the energy for you. Because maybe you hit the key in 2 milliseconds, but maybe it sounds for a minute. Well, depending on how you hit and depending on the instrument, but the energy is slowly released. And that's actually interesting. We see a violin here. A violin has a very low impedance to the string. The soundboard of the violin has a low impedance to the string, and the soundboard of the piano has a very high impedance to the string. At the violin, if you play it, the energy goes very easily towards the soundboard, and from the soundboard easily towards the air. With the piano, it goes very difficult towards the soundboard, and therefore it sounds so long. Furthermore, it colors the sound. And you can also hear this when I do this, I sound different. It's not only that I sound softer to myself and you hear me louder.
If I talk hello, I'm talking now with a paper in front of my mouth, well, it also sounds quite different, right?
Yeah,
Yeah.
exactly. Yeah.
Another example, yeah.
So it colors the sound.
Okay.
It colors the sound. Yeah.
So okay, those are the functions of the soundboard. what more can we say about it? So the soundboard is an important element in the piano.
Yeah, I think if you understand what impedance is, then you understand what the soundboard does, because all these aspects have to do with impedance matching, and phase shifts.
So that's really what we should talk about. Impedance. So impedance is a sort of resistance, a sort of hinder, more or less.
Yeah. And the way I usually try to explain this is with the swing.
Yeah,
so
we have
a couple of swings here.
Yeah.
And I would say, try to imagine the children's swing. So let's make a children's swing by removing some balls.
Yeah.
So here we have one swing.
Yeah. So this is a child. He's just swinging, and there's an adult pushing him. Okay.
Yeah. Well.
So what is happening?
It's a pendulum.
Yeah.
And a pendulum is an oscillator. It's just one oscillating system, and this pendulum has its own certain frequency. So we all know that if we drive this thing, that if we use the resonant frequency to keep driving it, it doesn't take much effort to do so.
So the resonance frequency is the frequency in which it
likes
favors
to,
the more.
Yeah, exactly. Yeah. So the admittance for energy in the resonant frequency is very high, and the impedance is very low. Admittance is the inverse of impedance. But now let's see what an oscillating system is, because all the systems basically do the same. You have a lot of forces working on this, but effectively some forces combined are the restoring force, and some forces combined are the continuing force. So if you find such a thing on planet Earth, then usually it is in vertical position.
Yeah, if no one is pushing it, then it's just hanging like this. Yeah.
It's where it ends because of friction.
It's not like, gravity is a bit high today, or
exactly.
Gravity has a different angle today.
Angle, no. Yeah. So so there are three forces that we deal with. One is the continuing force, one is the restoring force, and the other one is the force of friction.
Okay.
So what do we have here? Here we have the force of gravity and the force of the strings pulling it upwards to the center point. If we hold it like this, then we still have the force of gravity pulling it down. We have the force of the strings pulling it here to the center line. And these two forces combined form the restoring force, because it wants to go back here. If we hold the swing here, we fill it with potential gravitational energy.
Yeah, you're pulling it back, so
And if I let loose, it goes back to zero. But not only to zero, it goes further, because the kinetic energy here is converted into the potential energy here is converted into kinetic energy here. So the maximum amount of kinetic energy, the maximum height, the maximum amplitude, becomes, once it reaches the vertical position, the maximum kinetic energy. So
that is what makes it move. The kinetic energy is...
And the kinetic energy is driving the continuing force. So this is what happens with a swing. It will always...
go back and forth.
To the exact same amplitude, unless friction is involved. And friction is always involved, so it will end. But
so there's no such thing as a perpetuum mobile, or
no. But what is interesting, these are some forces. Okay, now let's first. Okay, let's say it. So you have the reactive component and the resistive component. The reactive component of the impedance has to do with the continuing force and the restoring force, how these two are tuned together. And the reactive component is talked about as the imaginary component of resistance. It is not resistance; it only changes the phase. But we'll get to that later.
All right.
So reactance, these two forces. Now the question is, you have this swing and it has its own frequency. Can we change this frequency?
This is the resonance frequency. we probably could if we just make if there are two. I mean, if this is a child, if there are two people who are just pushing it back and forth really,
Yeah, you can
really
increase
fast,
this frequency by maniacally just using a lot of force and energy to move this in a different way. But this thing doesn't want to. Of course, we can make it longer. Then in the case of the pendulum, we would just down increase.
Or shorter.
Or shorter, exactly, yeah. But if we don't do that, and in this case, that's the interesting thing. The length of the pendulum is the only thing that's of influence of the frequency, and that's because its mass is both a component of the restoring force, air, and also of the continuing force, also of the inertia. The inertia is the continuing force.
Yeah. So it doesn't really matter how heavy it is, or
no. Yeah. Even if you put two children in here, or two balls, maybe we can do that. Well. If it's not too much tight.
It's kind of
yeah,
we can make it work.
We can do that. So okay. So if we have one swing, it goes with this frequency, and if we have two swings, it goes with the exact same frequency. So the mass doesn't matter.
No.
But okay, that is swing specific.
All right.
Yeah. So every vibrating or oscillating object that there is in the universe has two of these forces working against each other, the continuing force and the restoring force. And in order to change it, we need to use a lot of energy. So if you want to make it go slower, you sort of hold this child against gravity and you let it down. You're working against which of the two forces?
The inertia.
No, the inertia is happy because you slow it down. You work against the restoring force. The restoring force wants to restore it, and you work against it. And if you try to speed it up, you're working against the inertia.
Yeah. All right.
And that's what you always do, and that's what the soundboard is always doing. And because of this, it has one specific frequency that it does like, and all the other frequencies are hard to induce into the system. So the soundboard, for example, has this very high impedance towards the string, but also at every point where the bridge is attached to the soundboard or the string is attached to the bridge or whatever, where the coupling is, the impedance towards the string should be quite equal for all the strings. And very high, and that's exactly this. And there's the other component, which is the resistance, which is why this eventually will stop, because this is not an elastic object, but a viscoelastic object, because there is a lot of heat being generated in these lines. Also, this frame is not perfectly stiff, and it is moving around in the viscoelastic gas, which we call air.
Okay, and so viscoelastic, that means
that it behaves partly elastic, so it has this reactivity in it, and it has some elasticity, and elasticity is a measure of stiffness of something. And it also has viscosity, and viscosity is where energy from one domain is converted into the other domain, into the domain of heat. You can measure friction with a thermometer. And in most practical systems, when it becomes heat, the energy is sort of lost, even though it still exists as heat, but it's not usable for us, so it's loss. And if we look at soundboards, we need a soundboard that has quite some reactance and also some resistance, because the resistance helps us to overcome problems, because if you induce a weird vibration that just doesn't sound good, the resistance will flatten it out. But the reactance makes it interesting. The reactance causes phase shifts and causes this character to appear, and also causes your tone to actually last long. If it was for friction, then it would just die out.
So it's reactant as well, and that makes it sound longer. And store is part of the storing of the energy, which you named as one of the functions of the soundboard in the piano. All right.
Yeah, what else can we say?
Maybe I don't know if there are some more examples about well the impedance match. We've talked about the if you make a funnel with your hands. So that's the thing that the soundboard does. So it matches the impedance of the string to the impedance of the air. It's sort of like a mediation between those two.
Yeah. Well, this is something that happens everywhere in the universe. You can have it with light, for example.
Okay, so light is also maybe a wave, or it can be particles, depending on.
That's not.
Okay, let's not go into that.
The ideology of light, but
Yeah.
but yes.
Okay, so how does it work with light? You also have to match impedance.
Yes, well, for example, if you are standing in the swimming pool, you look down, you think that your legs might be someone else's legs because they're standing in a weird angle from your body. That is a impedance mismatch because the light is going through the air, the medium air, towards the medium water, where there is no good match. So it's going in an angle, and also on the top of the water you see the reflections of your trees around, of yourself, etc. So so basically it goes into two directions. Same with the soundboard. Part of the energy of the string goes back into the string, so reflection, and part of the energy goes at a phase angle towards the rest of the system, towards the air. And also, for example, with lights, you also use these colored gelatin filters, to filter, to color, to create color, and that's exactly impedance mismatching or matching, or all impedance stuff related to do the same. So in all the domains, the same thing is happening.
Yeah. Well, that's interesting. Yeah, and good to see how this works in the piano. Of course, there are other components. You have to. Well, we've talked about a bit about strings, but mainly about the soundboard. But there's also, of course, the hammer and the keys and the piano action. I think we can leave that for another video, another discussion. So I think we've learned something about these different forces. So about the physics of the piano. Let's.
So now that you are on the playground, you understand what's happening when you're pushing a swing, and you also know how to build a piano.
Yeah, so. more or less. Yeah. So feel free to try and build a piano.
Yeah. Everyone should be able to do it right now.
Yeah, it's not that hard. Well, the principles behind it are maybe easier than you think. I mean, I think that's one of the main points that we're trying to get across here. So that it's based on these physical principles that apply to everything in the natural world, not just on the piano. So
this is really the most important part. But if you refer all this impedance stuff to the soundboard, you are really playing with filtering. That's basically one of the most important parts, because some soundboards just sound very, very ugly. And that is, if the internal damping is very high, which wood has a very high internal damping, so it makes it easy to make a soundboard, because if you don't design it so very well or don't execute it so very well, then the internal damping will help you a lot.
Yeah. So that's why a lot of soundboards are made out of wood, most of them.
And if you would use these high performance materials that we are working with a lot of composites, then it is really difficult to do it very well. The calculations need to be very, very good, and the manufacturing should be very good, because high performance composites use a lot of reactance for a big reactive component of the impedance, because that saves energy and because you can make more interesting stuff with it. But it's very easy to make it very ugly.
Yeah, because the internal damping is just a lot harder to get.
There's no internal damping in these kind of materials. So, well, there is some, but almost nothing. And that is the reason why most other composite instruments sound so very ugly because people are
Mhm.
treating it as if it's wood and it's not.
Yeah.
But by using the reactive components very well, you can get much, much more interesting results.
Yeah. So really, by understanding the physics of the piano, it is possible to use other materials and make an even better instrument.
Yeah.
Well.
Yeah, and in the case of composite, it's actually also interesting that that you can make it much more practical, not only better, but also more practical. I mean, you can put it in the rain even, or in the sun, or
yeah, it doesn't
whatever.
work the way wood does, so it's not.
It wouldn't crack from that.
Mhm.
You can put it in the oven, so that's fine.
Yeah.
And you can make it a lot lighter. But of course, always if you work with those kind of things, you just make it much more difficult to achieve good result.
Yeah. So I think that's a good conclusion to stop with. Thank you for watching. I hope you've learned something about the piano soundboard, and there will be some more videos in which we will discuss other components of the piano. So we'll discuss the strings and the hammer and the piano actions. So yeah, watch out for those videos. And for now, well, have a good day and see you next time. Thanks for playing.